chapter 4 is a very, very short chapter, and we're going to get through it relatively quickly. Our next test will be over chapters 4 and 7. Okay, so 4 has to do with electron domains and electron configurations within atoms, and then chapter 7 goes into naming. Okay, so they're kind of two different chapters. We're going to bunch them together because chapter 4 is pretty short. Okay, but chapter 4 today, we went over the math part, we went over molar mass, all that kind of stuff. Now we're going to kind of switch back to the atomic theory, and we're going to look at electron configurations basically within these atoms. We're going to start by looking at a couple different models of the atom. So what was the first atomic model that we looked at? What was that called? The Rutherford model, or the nickname for that was what? The planetary model, right? The Rutherford model, the planetary model. That was kind of the first one that we looked at. Today we're going to look at something called the Bohr model. Okay. The Bohr model tells us that electrons circle the nucleus only in certain allowed paths, okay, or orbits they called. Okay, so in the Rutherford model, we saw that electrons orbited the nucleus, but they kind of had that crisscross star pattern. Do you remember that? Yeah. In this model now, he says they have only very specific paths. They have circular orbits. So they're never going to crisscross each other. They're just going to orbit in these basically different energy levels here. Okay, the Bohr model shows us that we have lowest energy electrons when they're closest to the nucleus. Okay, so the farther that an electron gets from the nucleus, the more energy an electron has. Okay, so when they're in that orbit path that's close to the nucleus, you can think lower energy. Okay, he kind of described these energy levels, or these orbit levels, or these rings, however you want to say it, to kind of be like rungs on a ladder, right? Do you know what a rung is on a ladder? Like the steps, right? So his basic theory was that an electron can't be found in between these. They have to be on one level or the other. It cannot be floating in between, okay? Just like you can't stand on a level in between the rungs of a ladder. You have to be on one or the other. Okay, so that's kind of the way he described this energy level, is that you have to be on an energy level. You cannot be floating somewhere in between. The next model that we're going to talk about is called the quantum model. And we're going to talk about quantum numbers a little bit more in depth. And I'll just kind of warn you, quantum numbers are kind of abstract. Okay, they're a little bit hard to conceptualize, so please ask questions as we go along, because this will seem completely different and it will seem a little confusing at first. So please make sure that you're just asking questions as we go along. Okay, so the quantum model looks something like this. Okay, it's basically an electron cloud. This is a different model of the atom. So this is an indication as to where these electrons may be located. Okay, and it generally looks like this electron cloud. Okay, so the quantum model tells us the probability of finding an electron in the cloud surrounding a nucleus is proportional to the density of the cloud. So essentially, the darker the cloud, the more likely we are to find an electron in that region. Does that kind of make sense? Okay, so we are less likely to find an electron floating out here than we are to find an electron floating in toward the nucleus. Okay. And the quantum model gets more and more specific than this, but this is the general kind of outline for that. So the quantum number tells us the properties of the orbitals and the properties of the electrons within the orbitals. So does anyone know what an orbital is? Anybody have a guess? Yeah, what do you think?
Like the path in which an object orbits around another object.
Close. Okay, an orbital, yeah, what do you think?
It's in the shape of
We're getting there. Both of you kind of combined or together. So an orbital is kind of a little pocket that an electron can sit in. Okay? So an orbital is kind of like an electron holder. All right? And there's different orbitals that surround the nucleus of an atom. And they have different shapes, and they have different sizes. And we're going to be able to identify where these orbitals are located, how many electrons are in each orbital, and what shape that orbital is. Okay? So orbitals are kind of like electron little pockets, little holders for electrons. Does that make sense? So using this quantum number, so each individual electron has a quantum number, and it's going to tell you a couple different things. Okay? So each atom has 4 quantum numbers. They describe the energy level, the shape, the orientation, and the spin of the electron that's within that orbital. Okay? So a quantum number tells you a lot of information about where we can find that electron, what shape the orbital is, and the spin of the electron itself. Okay. Okay, so we know that each atom has these quantum numbers, and realistically, each electron within that atom has quantum numbers. Okay, because if we want to try to pinpoint the exact location of one single electron, we can use these quantum numbers to do it. Okay, it would tell us what energy level, the shape of the orbital, the orientation or where it sits around the nucleus, and then the spin of the electron itself. And we're going to go into each of these 4 parts into much more detail. Okay, but this is kind of an overlook or an outline of what we're looking at here. Okay. So the quantum number comes in 4 parts. Okay, we'll just give you 4 numbers listed in a row. The first number always tells us, or is called the principal quantum number, and it's symbolized by a lowercase n. Okay. Lowercase n tells us the principal quantum number. And what its job is it tells us the energy level of the electron. Is it close to the nucleus or is it far away from the nucleus? Okay, that's what that n number is telling us. Well, if I was going to look at a quantum number, this might be an example. Okay, I've got 4 parts listed there, and they each give a specific meaning. So I want you to kind of visualize this is what a quantum number would look like. Okay, does that make sense? Hopefully it gives you a little bit better picture. So this one is the one right now that we're talking about, is this principal energy level, and it would be labeled as an N. Okay, so when we're talking about a quantum number, this is an example of a quantum number. It's got 4 parts to it, and each of those 4 parts represent something different about that electron and about the orbital. Okay, so the one we're talking about right now is this N, okay, the principal energy level. Values of n are always positive integers because we cannot have a negative energy level. Okay, we can only have energy levels starting with 1. Okay, it can only be on the first energy level. There's no 0 energy level. Okay, so n has to be greater than or equal to 1. Okay. What n tells us is that if n is equal to 1, it occupies the first energy level, or the energy level that's closest to the nucleus. Okay? So if the electron we're looking at is on energy level number 1, that means it's in the energy level closest to the nucleus. Okay. It's also important for us to understand that electrons can have the same principal quantum number, right? They can have more than one electron in that lowest energy level. So quantum numbers for different electrons might look the same up until the last 2 numbers, okay? Or they might have similar parts to them, but they are not going to be exactly the same. Now let's talk about the second part of our quantum number. We're going to get through all of these parts, and then we're going to be able to look and do some practice, okay? So try to just kind of hang on while we're talking through all these, but please ask questions if you're not understanding something as we move through, okay? So the second part of our quantum number, out of the 4 parts, is called the angular momentum quantum number, and it's symbolized by an L, okay? This is not a 1, it's an L. Okay, and I usually do mine in cursive so I don't confuse it with a 1. Okay, but it is an L. Okay, and so that's called the angular momentum quantum number. And what it tells us is the shape of the orbital. So the first quantum number tells us how close that orbital is to the nucleus. The second number tells us what's the shape of the orbital that's holding that electron. Okay? So this is where it gets just a little bit more complex. Okay? The number of orbital shapes possible is equal to the number of energy levels we have. Okay, and let me kind of get through this and then we'll talk through it a little bit more. Okay, you can have values of L that are equal to 0 up to the number of positive integers that are n minus 1. So go ahead and get this stuff down and then we will kind of keep working through this together. Okay? Okay, so let's talk about what this kind of top bullet right here means. The number of orbital shapes possible is equal to n. So let's say that my electron that I'm trying to look at here is on the third energy level. That means n equals 3. Okay? If I'm on the third energy level, that means that I have 3 possible shapes for my orbitals. Okay? That's what it means when it says the number of orbital shapes possible is equal to n. So if my n equals 3, that means I have 3 possible orbital shapes. Okay? And then I can break it down a little bit further. Values of L are 0 and positive integers less than or equal to n minus 1. Okay? So let's look at an example. If n equals 2, L can equal either 0 or 1. Okay? So if n equals 2, that means that I can have 2 possible shapes for L, right? I can have 2 possible orbital shapes. And my values are either 0 or 1. Okay, I know this still seems abstract. We're going to get to that next part. Okay, I know that it still seems a little bit abstract. But if I'm on the second energy level, I could have 2 possible orbital shapes. One of those shapes is indicated by a 0, and one of those shapes is indicated by a 1. Okay? What'd you say? We will be able to look and we'll be able to identify one of those. Okay? So, if our n was equal to 4, what would be our possible values for L?
3, 2, 1, 0.
Good. L would be equal to 3, 2, 1, or 0. Okay? I have 4 possible shapes because n is equal to 4. Okay? L can be either 0, 1, 2, or 3. Okay, now is where it gets a little bit more tricky because your shape of that orbital is identified with a number. Okay, so keep these numbers in mind, right? If n is equal to 4, we're on the 4th energy level. That means we could have 4 shapes of our orbitals. Now let's look at how these numbers of L identify with a certain shape. Okay, because that's how it works. Okay. These are our L values. These are the letters or the shapes of the orbitals that go with them. Okay? I'm not sure why this is the easiest system that they could come up with, but it apparently was. Okay? So this is how it works. I'm sorry I didn't make the rules, but this is how it goes. So if our L values were 0, 1, 2, and 3, we would have these shapes of orbitals. An s orbital, a p orbital, a d orbital, or an f orbital, which is just crazy. We don't really deal with those very often. Okay, an f orbital has much different shapes. Okay. So in the s block, the electrons are going into s orbitals. In the p block, s orbitals are full, and now electrons will go into the p orbitals. And then the d block, s and p orbitals are full. New electrons go into the d orbitals. So let's look at your periodic table and identify what is the S block, the P block, and the D block. Okay? So let's look at your periodic table first, and then we'll kind of get to what's up here. On your periodic table, the S block contains groups 1 and 2. Okay? Groups 1 and 2 is the S block. So if you want to get your periodic table out and label that, I would do that. Okay? Groups 1 and 2 together make up the S block. Okay? Groups 13 through 18 make up the P block. 13 through 18 make up P block. Okay, so on your periodic table, you need to be labeling groups 1 and 2 are considered S block. Group 13 through 18 is P. And then all of the transition metals, 3 through 12, those are the D block. For the first energy level of electrons, only S orbitals are possible. So if n equals 1, L has to equal what?
0.
It has to equal 0, right? There's only one option because n equals 1, and L has to equal 0, which means it's an S orbital. Okay? So the electron there has to be in an S orbital or a circular orbital. Okay. And what we call that is the 1s orbital because it's an energy level 1 and it has to be an s orbital. So we call that a 1s orbital. We can name these orbitals now. If I had n equals 2, what would my L values be? My L would be 0 or 1. And what letter or what types of orbital shapes would those be? S and P orbitals. Okay, so in the second energy level, I can only have S and P orbitals. And isn't that true on our periodic table? Okay, in our second energy level, we only have S block and we have P block. Right? Okay, so that makes sense, does it? Maybe? 0 or 1, so that means we can either have S orbitals or P orbitals for the second energy level. It's a 1. That's called a 1s orbital. So the first energy level, which is hydrogen and helium, that's just 1s. Helium fits into the S block, okay? So that's a 1s orbital. When we move down an energy level, now we've got 2s or 2p orbital, okay? So that's what those are called, 2s orbital or 2p. So the 2s orbital would contain lithium or beryllium electrons. The 2p orbitals would contain boron through neon. For n equals 3, when we move down another sublevel or another energy level, we've got L equal to L is equal to 0, 1, or 2, which would correspond to S, P, and D orbitals. Right? So as we move down, we've got more availability for electrons to be stored. Okay, so when you look at the third energy level on your periodic table, which is sodium, magnesium, we've got 3s, which is sodium and magnesium, 3p, which is aluminum through argon, and then we also have the 3d orbitals, which are scandium through zinc. Okay? Yeah, that's right. So the third energy level has this what we call expanded octet, and those d orbitals kind of move up a row. So even though they're in the fourth energy level on your periodic table, they're part of the 3ds. Okay? And again, I didn't make the rules. Okay? So I don't know. The only reason for that is because it's got this what we call expanded octet. Once we get to the third energy level, then we really have more room for electrons to be stored. Okay? 3s, 3p, 3d. If I asked you for phosphorus, tell me exactly what block that is in. The 3p, right? 3p. So if I asked you for rubidium, what could you tell me about rubidium? what block would that maybe be in?
5.
The 5s block, right? It's in the 5th energy level, and it's still in the s block, so we'd be in the 5s orbital there. Okay? Okay. The third is called the magnetic quantum and number, and it's symbolized by an M. Okay, so values of M are only whole numbers, and they range from negative L to positive L. Okay, so there's a lot of possibilities for M. A lot of ways that that orbital could be oriented. Okay, the orientation of these orbitals depends on their shape and depends on the number of them. They have to be spaced evenly around that nucleus. Okay? So there's a very specific way that they have to fit together. That's why we use these M values. 108, 109 about magnetic quantum numbers might give you a little bit better visualization of that. Okay, so I want you to read through 108 and 109 about magnetic quantum numbers. Okay, so did that give you a little bit better picture about these magnetic quantum numbers? They can be on different axes. Okay, so that orientation depends about how many orbitals there are there and in what orientation they are. So they have to fit together kind of like a puzzle. It does make a difference about what energy level we're in because there's more room as we go down the periodic table or as we increase energy levels. Okay, so if n equals 1, that means L is equal to what? Only 0, right? When in what would be the name of that orbital? What would we call that orbital? Yeah, it would be an s orbital, so we'd call it a 1s orbital. Okay? What would m have to equal there? Yeah, it'd have to be 0, right? There's no orientation because that's the only way that that orbital can be is a spherical shape. Okay? If n equals 2, L is equal to either, 0 or 1. Okay? That means we've got 2 possible shapes. So let's say our quantum number started out like this. 2, 1. What would our m value possibilities be? Okay, if L was equal to 1, m could range from -1, 0, +1. Okay, and that's kind of the example that they gave in the book. So this would be what type of an orbital, an s, a p, or a d orbital? Do you know? A p orbital. You're exactly right, okay? If L is equal to 1, then it is a p orbital. So we've got 3 different orientations that our p orbitals could sit in. Okay, and that's what the m value is telling us. Our p could either be sitting on the x-axis, on the y-axis, or on the z-axis. Okay? Believe me, I know that this is so new, and it seems so strange. I get it. Okay? I promise we're going to get to a point where you feel like you know what's going on. Okay? So please just hang in there for a little bit. Okay? Our spin quantum number, all this tells us is that each electron within our orbitals has a certain spin. One spins in the positive direction, one spins in the negative direction. Okay? So each of our electrons within an orbital has a spin. Okay? One has to spin in the positive direction, one has to spin in the negative direction. So something that I should tell you again about orbitals is that orbitals can only contain 2 electrons. So these little pockets, these little electron holders, they can only contain 2 electrons. One has to spin in the positive direction, one has to spin in the negative direction. Okay, so orbitals themselves can only hold 2 electrons. Okay, so we talked about each orbital itself only being able to hold 2 electrons. Okay, that means when we look at these p orbitals, the px orbital can hold 2, the py orbital can hold 2, and the pz orbital can hold 2. Altogether, the p block holds 6 electrons. Okay, and that is what we are concerned with. We're not going to break them down into pxy, 3px, 3py, and 3pz. We're not going to do that, but you need to understand the p block itself can hold 6. The S block itself can still only hold 2. The D block itself could hold 10 electrons. So each of those, D, X2, Y2, we're not going to get really into all that, but you need to understand that the block itself can hold 2, 6, or 10. So if you look at your periodic table, the S block has 2 elements. So think about it like that. It can hold 2 electrons. The P block has 6 elements, which means it can hold 6 electrons. Okay, so the periodic table lends itself well to remembering those patterns. Okay? So here's kind of an example of what we were looking at and how we labeled our periodic table. All the pink ones fall into the P block, the blue ones fall into the S, these orange are the D block, and then the lanthanides and the actinides are the F block. So if you want to label those, you can.
I thought helium was an S block.
Yeah, we really do pull it over here for the S, okay? Because it's on the first energy level. See how it's labeled 1s2? That means it's still part of that S block. It just sits on the periodic table on the right-hand side. Okay, so it's in the first energy level, which can only have an S orbital, so it has to be part of that S block. Good question, though. Okay. So when we start to talk about our electron orbitals and we're trying to locate an electron, we use what's called an electron configuration. And we use this kind of long string of numbers to tell us where these electrons are located. Okay, so here is how we label these specific blocks, right? We said helium kind of pulls over and becomes part of the S block because it's in the first energy level, which can only be an S-shaped orbital. Okay, then as we move through these, we see the 2p orbitals, the 3s orbitals, 3p, and then 3d, 4s, 4p, okay, blah, blah, blah. Our overall goal that we're going to look toward here is we're going to be able to locate an electron of an atom. So I might say, what's the electron configuration of bromine? And you're going to tell me it's got electrons in the 1s block, and then it has electrons in the 2s block, and the 2p, and the 3s, and the 3p, and then 3, right? All of those orbitals have to be filled underneath before we can get to our outer shell orbitals. That's kind of our overall goal here, is that we have to fill these bottom orbitals first before we can start building outward from the nucleus. So we're going to be able to identify each electron in an atom and tell me where it's located and in what orbital, what energy level it's on, all that kind of stuff. Okay, but we had to work through quantum numbers to get to this point. Okay? Okay? We're getting there? Good. Okay. So now we're going to get to basically the goal for today. I know we had to get through a lot of stuff to get there, but this is our take home for today, kind of. Okay, it's something called electron configurations. And they tell us the electron arrangements within an atom. So it's telling us what orbitals have been filled, what are still empty, right? What has some room for some more electrons, all that kind of stuff. Okay, is electron configurations. When we start to put in our electrons, we have to fill the lowest energy levels first. So if we're starting to look at selenium and we're trying to build our build our atom, we have to fill the electrons into the bottom levels first. Okay, so you can't start at the top and work your way down. You have to start at the bottom and build your way up. Okay, so that means electrons have to fill the lower energy levels first before we can get to the outer shells and the outer portions of that atom. Okay, so we can't have empty orbitals that don't contain electrons toward the nucleus, right? We have to build from the inside out. Okay, so what we are looking to identify here or to write are what we call ground state electron configurations. And that just means without a charge, right? They're in their ground state. They're not charged. They're not ions at this point. They're just regular plain old elements. Okay, so this kind of diagram gives us, can you see what these little numbers say? Right? 1s, 2s, 2p, 3s, 3p. Okay, we have to fill the lower energy orbitals first. So we cannot have an element with 6 or with 5p electrons without filling every single one underneath of these first. Okay, and this is called the Aufbau principle. Okay, he says that lower energy orbitals have to be filled first. So each of these lines right here represents an orbital. And how many electrons can be in each orbital? 2, right? There could be 2 electrons in each single orbital. Okay, so if we were trying to look at the atom silicon, okay, sorry, I'll give you a second to finish getting this written down. Okay, so if I wanted to locate the outermost electron for silicon, I want you to try and determine what orbital that would be in. Okay, would it be a 1s? Would it be in the 6p? Would it be in the 5d? Where do you think that silicon outermost electron would be? Okay, yeah, Sean, what do you think? So, what do you think?
3p.
The 3p. Perfect. Okay? And tell me why it's in the 3p orbitals. Third energy level, good. It's in the p block. That's perfect. Okay, so let's kind of look. I'm just going to show you this diagram real quick. This is nothing that you need to know how to do at this point, but I'm just kind of showing you how this works. So I know silicon is going to be in the 3p block. Okay, it's going to be somewhere here. The outermost electron for silicon would be located in the 3p block. Okay, so that means I have to fill my other electrons first. Can somebody tell me how many electrons silicon has total? 14. Okay, and I so far have 2, 4, 6, 8, 10, 12. I need 14 electrons, so I'm going to add one more to each orbital. Okay, does that give me 14 total? And I'm in the 3p orbitals? Yeah? Okay, very good. So this is going to be your cheat sheet that's going to show you which orbitals need to go in what order. Okay? And so this you can keep with you. You will be able to use this on tests. But what this tells you is kind of the order in which you're going to fill electrons. And I'll show you how you follow this line. There's going to be extras in the back. I'll come collect them in a second. So what this tells us is that we need to fill the 1s orbitals, then we fill the 2s, then we fill 2p, then 3s, then 3p, then 4s, then 3d, then 4p. Okay, so all you're doing is following this line. That tells you exactly the order in which these orbitals have to be filled. Okay, so it doesn't go 3s, then 3d, then 3p. That's not how it works. Okay, and that has to do with the size of the orbitals and the way in which electrons have to fill those energy levels. But this is the order that it goes in. Okay, so when you start to look and write electron configurations, you're going to go 1s, then 2s, 2p, 3s, 3p, 4s, blah, blah, blah. Okay, you're going to work through that kind of cheat sheet. Does that make sense? Okay. So here are some electron configurations, and this is what we're working with right here to begin with. This is our goal today, is to determine these electron configurations. So let's look at hydrogen, okay? The electron configuration for the outermost electron of hydrogen is 1s1, okay? Why do we think there's a 1 right here? Yeah, there's only one electron in hydrogen, right? There's only one electron. So that means this 1s orbital contains one electron. That's what it's telling us. Okay, so that superscript tells us that in that orbital, there's only one. Okay?
Well, that makes everything else make sense.
Okay, so now for helium, it's in the 1s orbital, but how many electrons are in that orbital? 2. Okay, and how many electrons can each orbital contain? 2. Okay, now let's move down here to lithium. How many electrons does lithium have total? 3. So lithium has the 1s block has 2 electrons in it. And then we move down to the 2s, and it has 1 electron in that 2s orbital. Isn't that exactly where lithium is on the periodic table? 2s, 1. That's it. Okay, so your periodic table is going to tell you these electron configurations. Okay, let's skip down to nitrogen.
Do we always have to label like that 1s part first?
Mm-hmm. Yep, so it always has to go in that order along your cheat sheet. Okay, nitrogen. Let's look at nitrogen. How many electrons should nitrogen have?
7.
It should have 7, right? Because that's its atomic number. And it's a ground state, so it's at neutral. So nitrogen has to fill the 1s orbitals, which it does. Then it fills the 2s orbitals, right? 2s2. And then it goes to the p block, 2p. 2p, 1, 2, 3. Okay? How you feeling? Okay, so we use our cheat sheet, and we have to fill the 1s orbitals first. So let's look to find where magnesium is on your periodic table to kind of see what your goal is here. Okay, magnesium is in what block? The 3 what? The 3s, perfect, okay? So that means we need to fill all the orbitals up to that point, which means we need to fill the 1s, and those are full, so that gets a 2. 2s, those are full. Are the 2p orbitals full?
Yes.
2p, so that would be a 6. Okay, because the p block can hold 6 total electrons. 3s. And magnesium, does it have 1 electron or 2 electrons in that 3s?
2.
It has 2. So now we go back to check ourselves. How many electrons should magnesium have? 12, right? So 2 plus 2 plus 6 plus 2 equals 12 electrons. So you have a way to check yourself. 6 is the absolute most that the p orbitals, yes, could hold. The d block can hold 10, because there's 5 different orbitals there. The f block can hold 14. Yeah, so you go back to your cheat sheet. So after the 3s orbitals, you would go 3p, and then you'd go 4s, then 3d, then 4p. So you follow along that path. Okay? That feeling a little bit better? Kinda? Okay, let's try some more. Yeah, Laura, what's up? Yeah, we're going to do a couple more. Okay, let's do potassium now. Oops. So I think your best bet is to find where potassium is, then you want to fill all those before that. Okay, so you can work your way to potassium. So our 1s orbitals are full, 2s, 2p orbitals are full. Are the 3s orbitals full?
Yeah.
Yes, so we go 3s2. 3p orbitals, are they full?
Yeah.
And what about the 4s orbitals?
1.
We only have 1 electron in that 4s orbital because it is the first element in that 4s block. So it only contains 1 electron in that 4s orbital. No, on your cheat sheet it tells you the order. So the d orbitals don't get filled until the 4th energy level. Okay, so you follow along like this. You go here, and you follow, okay, so you go 3s, 4p, 3p, then 4s, and then you go 3b, then 4p. So it goes that. Okay, so then you check yourself with your superscripts. Okay, so 2 plus 2 plus 6 is 10, plus 2 is 12, plus 6 is 18, plus 1 is 19. Does that match potassium? Excellent. Okay, so what this is telling us is that the outermost electron for potassium is located in the 4s orbital. So it's in the 4th energy level, and it's in a spherical orbital. Okay, that's what those numbers tell us. Okay, feeling okay? Okay, this was our overall goal. I told you it takes a while to get to our final goal here. Let's try these last two on your own. Okay, calcium and silicon. If you have questions, please raise your hand and I'll come around and help you with those.
1s2, 2s2, 2p6, 3s2, and then 3p2.
3p2, perfect. Very good. Configuration. So we can abbreviate them by using a noble gas. Okay? To abbreviate. Can anyone think as to why we might be able to abbreviate with a noble gas? Yeah.
The noble gas is all its noble moles.
Perfect. Perfect. A noble gas has a full octet or a full shell, right? A full outer shell. Nothing available to bond with. So if we know that it's got the same electron configuration as that noble gas, kind of up to that point, we'll be able to just build on that. Okay? So if we want to define the electron configuration of calcium, this is how we would find the abbreviated one. Okay, so let's look at calcium on your periodic table. What's the noble gas in the energy level above that? Argon. Okay. So the way we would abbreviate this is we would say our electron configuration is the same as argon plus whatever goes after it. Okay, so after argon, what needs to be filled in order for it to indicate calcium? 4s2. Very good. Okay, so that's how we do abbreviated. This is sometimes called noble gas configuration or abbreviated electron configurations. There's a couple different names for this, but we're essentially abbreviating these electron configurations with a noble gas. Okay. If I ask you for the abbreviated version of krypton, you can't just say krypton, right? That's not how it works. Okay, so you would have to tell me argon and then build from that. Does that make sense? So if you wanted to look at an abbreviated, if I wanted to ask for an abbreviated or a shortened version of helium, you couldn't do it, right? You would have to just say 1s2. There's no abbreviated version for anything that's similar.
Is that why can you abbreviate with the noble gases?
Because the noble gas has a full octet or a full shell, we know that the electron configuration is going to be exactly the same up to the point of argon, and then it's going to be plus some extra. Okay?